All right, you guys, part 2 of these 2.2 notes where we have moved on to this power rule, which makes finding derivatives so much faster than the limit process. So I'm going to show you an example. This is not in your notes. This example that we're looking at right now is actually from 2.1 where we did the limit process. So this is just a quick screenshot that I took of the notes from that section, where we look at our function f of x and we applied the limit process where we took f of x plus delta x. So you can see where I'm showing that x plus delta x right now minus f of x itself, all divided by delta x. So then we expanded, simplified, and finally we're able to use direct substitution for x and for delta x, where we got our derivative 6x minus 2. And then in the first part of this notes that you guys have already watched right now, we learned this incredible shortcut called the power rule, where if we have a function that is simple enough to be written as powers of x, then we can apply this power rule. So f prime of x, so all I've done right now, I just rewrote our original function, f of x, which was 3x squared minus 2x plus 1. We have this derivative, or this limit process here, which gets us to our derivative. And now we have the awesome power rule, which says we take the power of x, bring it down and multiply it by the coefficient. That would be 6x. And then we reduce the power by 1. So instead of squared, it would now be to the first power. Then I take the derivative of negative 2x, which is just minus 2, because the slope of negative 2x is always negative 2. And the derivative of any constant is always 0. So in a matter of seconds, we get to this derivative using the power rule. It's important and valuable to be able to use the limit process because this is the definition of a derivative. This whole limit process was derived from using the slope formula of a tangent line. But this awesome power rule gets us there much faster. So we will be using that. Today we're going to move forward and learn some more formulas for derivatives, specifically sine and cosine. So let's flip on over and see what those derivatives are. All right, so the derivative of sine and cosine, they're very simple, and you might even be interested in finding out why this is the way it is, but the derivative of sine is cosine. So if you can visualize the two functions together, we've got sine. I'm just going to graph them really fast. I'll put sine here. So here will be pi and 2 pi. So the sine function, that was terrible. Let me try that again. Sine function goes like this. Okay? And the cosine function goes like this. Okay, so when we think about derivative of sine, so sine is the blue function, remember. If I'm thinking of derivative of sine, that's going to tell me the slope of the sine function at any given point. So let's say I wanted to know the slope of the sine function right here. In order to find that, since its derivative is cosine of x, that means if I wanted to find the slope at that red point I just put, all I would have to do is plug my x value into the cosine function, and whatever that y value is right there, almost 1, let's say it was 0.8, I'm just guessing, that would mean that's the slope of my sine function right there. I use the y value of the cosine function, and that gives me the slope of the sine function at that x value. And then if we look at the derivative of cosine, which happens to be the negative value of the sine of x at that x value, it works the same way. So if I wanted to know, let's see, here is, let me just put a point right here on the cosine function. If I wanted to know the slope of the cosine function right here, clearly it's going downward, so it would be a negative slope. If I wanted to know the derivative or the slope of this function right here, all I would do is plug this x value into my sine function, so this x value into the sine function. So it looks like I'm almost at 1, and then negate it because it's negative sine of x. So this would mean the slope right here is almost -1. So that's how the derivative of sine and cosine work. You don't have to really, this visual is just kind of help you to understand how this could be. I wanted you to see that visually it does work out. But you just have to remember that the derivative of sine is cosine, and the derivative of cosine is negative sine. So let's apply that here to some examples. So in example 1, we're looking at f of x equals 2 sine of x. The 2 is the coefficient, and that will just kind of be along for the ride. So the derivative of f prime of x, the derivative of f prime of x is 2 times the derivative of sine, which is cosine. So the derivative is just 2 cosine of x. If we look at number 2, we've got a little combo. So we've got 3x plus cosine of x. So again, I'm going to take the derivative of 3x and then take the derivative of cosine of x, which is negative sine of x. So you're going to want to continue to refer up to the top of your page right here. And eventually you won't need to look back up because these are very easy to memorize. But you always have those up there to refer to. So the derivative of number 2, f prime of x would be the derivative of 3x, which is just 3, plus the derivative of cosine of x, which is negative sine of x. So it would just be minus sine of x, and that is the derivative. Number 3, so we're going to see a slight increase in just the level of difficulty as we go. So cosine of x over 5, we want to rewrite that as 1/5 cosine of x. So whenever possible, rewrite these functions as a coefficient rather than division if possible. So let's rewrite this function as 1/5 cosine of x minus 3. So now when I apply the derivative of cosine, which is negative sine, this 1/5 is just out front along for the ride. The derivative of negative 3, which remember the derivative of any constant is just 0. So then this would give us our final answer, f prime of x. Derivative of cosine is negative sine, so this would be negative 1/5 sine of x. Or you could write it as negative sine of x over 5. So we also could have written this as negative sine of x over 5. So those are the same because this sine of x is technically over 1, and we could just combine that into a single fraction if we wanted to. Number 4. So now we're looking at a fraction with x in the denominator plus 2 cosine of x. To find the derivative here, again, to find the derivative of the first piece, find the derivative of the second. But the first piece is not written as x to a power, and because the only tools we have right now is the power rule and the derivative of sine and cosine, we need to rewrite this function as x to the -1 plus 2 cosine x. Because, again, in order to use the power rule, we need to be able to write it as x to a power, and 1 over x to the first is the same as x to the -1. Now we can apply power rule to get f prime of x, which is, I'm going to take the negative down front, so that would be negative x, and then subtract 1 from -1, and you get negative x to the -2. And then I'm taking the derivative of 2 cosine x, so we look back up, derivative of cosine is negative sine, so the derivative of 2 cosine is going to be -2 sine of x. Okay, so I'm not totally finished here because our final answer shouldn't have any negative exponents in it. So instead of negative x to the -2, we can rewrite this as -1 over x to the +2 minus 2 sine of x. All right, moving on to number 5, we've got x squared minus 3 over x. So again, we want to think, can we directly apply power rule? Yes, we can to x squared, But for negative 3 over x, we need to rewrite that piece. So I'm just going to rewrite the function as x squared minus 3x to the negative 1. So again, we're rewriting 3 over x as 3 times x to the negative 1. Now we can apply the power rule. And that would be, oops, f prime of x equals 2x to the first, applying power rule to this first piece. And then here, so what I'm going to do is take the negative 1, bring it down and multiply by negative 3, and that actually gives me a positive 3x to the negative 2 once I subtract 1 from my original power there. So I'm done applying power rule. We just need to rewrite because I've got a negative exponent. So this would give me my final answer of 2x plus, instead of 3 times x to the negative 2, it would be 3 times 1 over x squared, which can be rewritten as 3 over x squared. And that's it for that one. Number 6, when we look at f of x, we see a large fraction. Many of you will shut down and say no thank you. But here, we can actually simplify this fraction very, very easily so that we can simply apply the power rule. So remember that with fractions, if you've got a single denominator, you can actually split this into 3 different fractions. So we can rewrite this whole function as x cubed over x squared plus 4x squared over x squared minus 6 over x squared. Just like if you have the same denominator, x squared, you can rewrite that as a single fraction over x squared. We're just going in the opposite direction, and we're taking each of the 3 terms in the numerator and breaking it apart into 3 separate fractions. Because when we do that, this simplifies. So this actually gives us a function f of x. And when we simplify x cubed over x squared, that's just x to the first, so that would be x. 4x squared over x squared is just 4, so plus 4. And then we have 6 minus 6 over x squared. I just need to write that as minus 6 times x to the negative 2. So what we've done is rewritten, split this apart into 3 separate fractions, and then simplified each of the 3 fractions to something we can apply the power rule to. Now I can take the derivative, and that would be f prime of x. The derivative of x is just 1. Again, we're thinking slope, right? This is originally to the first power, so we bring the 1 down out front and multiply it by x to the 0, which is 1 itself. So that would just be 1. The derivative of 4 is just 0. And then I apply the power rule here, and I would do negative 2 times negative 6. And that would give me a positive 12 x to the negative 3 when I subtract 1 from negative 2. So this is it, but I do need to rewrite x to the negative 3 as 1 over x cubed. So let me just simplify, and my final answer will be 1 plus 12, instead of times x to the negative 3, it would be divided by x to the positive 3. Okay. Okay, just a couple more examples here with sine and cosine, and then we'll move on to another type of problem. So in number 7, we've got 5 root x minus 6 sine of x. Remember, in order to apply, so we can differentiate negative 6 sine of x because we know the derivative of sine is cosine, but this is not written as x to a power, so the first thing we need to do is just rewrite that. So this would be, when we rewrite this function, it would be 5, instead of the square root of x, it would be x to the 1/2 minus 6 sine of x. And now I can use power rule. So the derivative of this would be, when I apply power rule, I'm taking the 1/2, the original power of x, and multiplying it by 5. So it would be 5/2 x, 5/2 x, and then subtract 1 from 1/2, and it would be x to the negative 1/2. And then I take the derivative of negative 6 sine of x, and derivative of sine is cosine, so that would just result in negative 6 cosine of x. Okay, but I'm not done because I have this negative exponent. Okay, I have this negative exponent here. We know x to the 1/2 is the square root of x, so x to the negative 1/2 would be the square root of x in the denominator of a function. So to simplify this final answer, 5 is in the numerator, 2 is in the denominator, along with x to the 1/2, x to the positive 1/2, which we can either write as square root of x, or you could have just left that as x to the 1/2 down here, or square root of x, it doesn't matter. And then minus 6 cosine of x. Okay, I want to do this last example, number 8, just because I'm dealing with 2 different roots other than square roots, and I think these problems here are ones that people typically just kind of shy away from. So again, before we can even apply the power rule, we need to first rewrite this as x to a power. So instead of cubed root of x, we would write x to the 1/3, and minus, instead of 4th root of x, we would write x to the 1/4. Now we can apply power rule. So f prime of x, applying the power rule, I take the 1/3 and bring it down, times x to the 1/3 minus 1. So that would be negative 2/3. Whoops. Hold on, I messed up my little 1 here. 1/3 times x raised to the 1/3 minus 1. So I'm going to write this out. Some of you will jump right to negative 2/3, but I'm going to write it out as 1/3 minus 3/3, just so you'll see how we come up with negative 2/3. And then for the second piece here, I bring down, it's minus because of this minus, so don't lose track of those. I bring the 1/4 down in front, so that would be minus 1/4 x raised to the 1/4 minus 1, which is going to end up being negative 3/4. I'm going to actually write it as 1/4 minus 4/4. So if you get confused with taking a fraction and subtracting 1, I would encourage you to write this step out where you, instead of writing minus 1, you're writing minus 3/3 or 4/4 or whatever makes the subtraction easy. So let's see what that gives us. So this would result in 1/3 x to the negative 2/3 minus 1/4 x to the negative 3/4. Okay, so we're not done yet because I still have negative exponents in my final answer. So now we just need to take that negative 2/3 and negative 3/4 and rewrite as 1/x to the positive of those fractions. So that would give us a final simplified answer of the numerator from the first one is still 1. 3 stays in the denominator, so that would be 1/3x to the positive 2/3 minus 1/4x to the positive 3/4. And you can leave your answer like this. It's fine to have these fractions in the answer as long as they don't have the negative exponent. That would be fine. So you can leave it like that. Okay, so this last set of problems is finding the equation to the tangent line. And remember, a tangent line we can find because the slope of the tangent line is the derivative. So that's the important thing to remember here. The slope of a tangent line is the derivative of a function. So tangent is f prime of x. And once you know the slope, you have this point here and you can just use that to find the rest of the equation. So with number one, we want to find the equation of the tangent line. So first of all, equations of lines, we need to remember that's always y equals mx plus b. So we are looking for the equation of the tangent line to this graph at this exact point. Let me show you a visual of that. Okay, so here's a screenshot of this graph from my calculator. So this is this function right here, x cubed plus 2x minus 1. This problem is asking us to find the equation of the tangent line to that curve at the point 1, 2. So we see the point 1, 2 is on the curve right here. And this problem is asking for, so what is that exact equation of the tangent line? The line that just grazes the curve at that point. It's hard for me to get it exactly right, but you know what I mean. So the curve at that point. Well, now that we have this power rule, this should be a pretty quick process for that, because we know that the derivative will tell us the slope. So this m is coming from f prime of x, but specifically f prime of 1, because when the x value is 1, that's where the tangent line is. So we really want f prime of 1, and that's going to tell us the slope of this line. So let's find f prime of x. We can apply the power rule and get that the derivative of our function is 3x squared plus 4x to the first plus 0, because the derivative of -1 is 0. So this is our derivative, but I want to know the slope. That would give me m for the equation of our tangent line. So I'm just going to plug in 1 for that. And the reason I'm plugging in 1, again, is because this is happening when x equals 1 right there. So that would be 3 times 1 squared plus 4 times 1. So the slope of our tangent line is 3 plus 4, which is 7. That makes sense visually. So look at our graph. That tangent line is positive, pretty steep, growing pretty quickly. So I'm almost to the point where I have the equation of that exact tangent line, because I have 7x plus b. Now we just need to find b, and we know the y value of our point because we were given this whole ordered pair 1, 2, which means I can just plug in 2 for y, 1 for x, and then solve for b. So 2 equals 7 plus b, which means I would subtract 7 from both sides and get that b equals -5. Again, going back to our visual, that should make sense. -1, 2, 3, 4, 5. So this tangent line would cross the y-axis at -5, which lines up with our graph right there. So this equation of the tangent line, we found the slope by finding the derivative, because that's what derivatives tell us. So that would be 7x minus 5. So that's the equation of the tangent line on the graph right there. So the slope is what the derivative told us, but then we could take it one step farther and find the actual equation of that line. I really like problems like these because it's kind of a big overall picture of what this derivative is telling us, and it links it back to that tangent line. All right, let's try a couple more. So flip it on over to the next page. All right, so these next 3 examples are all still under those directions of determine the equation of the tangent line to this function at this point. So let me just write that in here so we remember what we're doing. Okay, so we're finding the equation to the tangent line to this graph at this point 8, 1/2. So let's look at what this graph looks like. Okay, so here's a visual of the graph that I'll just put over here. So it's 1 divided by the cubed root of x. And these, even though it cuts off right here, these continue. They just get very, very, very infinitely close to 0. So we're looking for the equation of the tangent line to this graph at 8, 1/2. So obviously 8, 1/2 is on this curve right here. So 8, 1/2 would be right here where my cursor is right here. And we're asked to find the equation of the tangent line right here. So this tangent line is very level looking because it is decreasing at this point, but it's by here it's decreasing very slowly. So that we should expect that slope to be negative, but to be really close to zero, but negative. And in order to find the equation of that tangent line, so remember our answer is going to be in the form y equals mx plus b, and the m, the slope of that, is coming from the derivative of f of x. Before we can find the derivative, we need to, in order to be able to apply the power rule, we need to rewrite this as x to a power. So 1 over the cubed root of x, I'm going to do this in 2 steps just to make it clear. First, I'm going to rewrite the cubed root as 1 over x to the 1/3. And then I can rewrite that as x to the negative 1/3. And a lot of you may have jumped from this to x to the negative 1/3, which is fine. I just want to show the process so that you guys are following every step. So to find that slope of the tangent line, we need to take the derivative, and I'm going to apply the power rule. So I pull down the negative 1/3 x in front, and then I'm going to subtract negative 1/3 minus 1. So negative 1/3 minus 3/3. And that's going to give me a final derivative of negative 1/3 x to the negative 4/3. Okay, so this is giving me the formula for the slope at any possible value of x. Specifically, I want the slope when x is 8. So instead of simplifying this, you can just crunch the numbers now because we just want to know the slope, the actual value when x is 8. So you can just use your calculator, plug in 8, raise it to the negative 4/3, and make sure you put the negative 4/3. That exponent in your calculator is going to need to be in parentheses. So make sure you enter it all incorrectly. It's negative 1/3 times 8 raised to the negative 4/3, and that's going to give us our slope. Another way, since I know none of you are reaching for your calculators right now, you're just waiting for me to do this. Another way we can think of this is rewriting what I have going on here. So I'm going to go through the step-by-step process of doing this by hand, and I know you're all thrilled about that. So I'm going to rewrite this as negative 1/3 times 8 to the positive 4/3. And that we can figure out because negative 1/3, 8 to the 4/3. Think about that. That is actually 8 to the 1/3 and then raised to the 4th power. And 8 to the 1/3 is the cubed root of 8, which is 2. And then I'm raising that to the 4th power. So this 8 to the 1/3 simplified to 2, and then I'm raising that to the 4th. So this is actually, the slope is actually going to be negative 1/3 times 16, so negative 1/48. All right, so this, we use the power rule, we plug in 8, it's a hot mess because of all the fractions. We can use our calculator or do it by hand because we are smart, and then we evaluate and we get negative 1/48. Okay, so all I have now is the slope. It's negative 1/48, slope of my tangent line. I told you it was going to be really close to 0. Look how flat that curve is right there. But it is slightly going down, so it's a very, very small negative number. So that negative 1/48 should make sense to us. Now I just need to figure out the rest of the equation of that line. I'm trying to move this graph, and I can't. Okay, so I had to get rid of the graph, but I'll pull it back up in a minute. All right, so again, we want the equation of the line. Right now we have the slope. So I'm going to rewrite what we have. We've got negative 1/48 x plus b, and we have this ordered pair. So I have an x and y that I can plug in here and here. So we can plug in 1/2 for y, 8 for x, So that's times 8 plus b. We end up with 1/2. Negative 8 over 48 simplifies 8 over 48. That's 8 times 6 is 48. So that would be negative 1/6 plus b. So to get this, I need to add 1/6 to both sides. So I need to add 1/6 to 1/2. And I can rewrite 1/2 as 3/6. Okay, so 3 over 6 plus 1 over 6 is 4 over 6, which means b equals 2/3. Okay, wow, you didn't think you'd be doing so much work with adding and operations with fractions. Okay, this gives us our final answer. So this gives us our final answer for the equation of this line. Y equals our slope of negative 1/48x plus 2/3. Now I'm going to pull that graph back up and make sure that that lines up. Okay, here's the graph, and I'm going to cover all that up for a second. Again, we were talking about the 0.8 1/2, which was right here, and it was a very flat, slowly decreasing curve. And that has a slope of negative 1 over 48 and a y-intercept of 2/3. So that perfectly lines up with this visual that I pulled up. So hopefully you guys are following this. I love problems like this. You'll hear me say that every time because it just makes us look at the whole picture of what a derivative is, what it tells us about a function, its rate of change, that tangent line, the equation of the tangent line. It's just some good stuff. Okay, let's look at one more of this type. I'm going to jump down to number 4. If you're enjoying this as much as I am, definitely work through number 3. You can do this. Before you apply power rule, you have to distribute and work that out. Apply the power rule and get the equation of that line. I'm going to move on to number 4 for now because it's got a trig function in it. Okay, number 4. We're looking for the equation of the tangent line to this function at 0 when x equals 0. So think about what this function looks like. It's the sine function, and it's been shifted up vertically by 1. And I want the equation of the tangent line when x equals 0. So the equation of a line, always remember that's just y equals mx plus b. And now that we know what derivatives are and how to find them, we can determine the value of m pretty quickly. So the value of m is going to come directly from the tangent or the derivative of f of x. So I'm going to take the derivative piece by piece. The derivative of 1 is 0, and the derivative of sine is cosine of x. So this function actually just has a derivative of cosine of x. But I want to know the derivative specifically when x equals 0, because that's going to give me the equation of the slope of the tangent line to the function at 0. So I'm just going to evaluate f prime of 0, which is the cosine of 0, which I know you all can do, because the cosine at 0 has a cosine of 1. So this has a slope of 1. We have a equation y equals 1x plus b. Then to find b, all I'm doing is plugging in the ordered pair, but look, we don't have an ordered pair. All I have is 0. Can I figure out the y value when x equals 0? Yeah, just plug 0 in for x, and then we'll get the y value. We'll get f of x. So that would be 1 plus sine of 0, and sine of 0, look down here, I already have 0, cosine is 1, sine is 0. So that y value is just 1 plus 0, which is 1. So the ordered pair, even though it didn't give us the ordered pair, it's 0, 1. It only gave us the x value, but we have enough. All we have to do is plug that x value in to get the y value for our function. 0, 1. All right, so now I can plug that into my equation of a line. When x equals 0, y equals 1, which means b equals 1. So b equals 1 and the slope was 1. We found the slope here, we found b here, so the equation of our line equals 1x plus 1. So I just wanted you to see an example with a trig function here, and one that didn't give you the whole ordered pair. You just plug in the x value to get the other half of it. Okay, this last concept, finding the points at which a function has a horizontal tangent line. Before I jump into number 5, where would a function have a horizontal tangent line? Let's say I have something like this. Let's think about slopes of tangent lines. So here's a tangent line. There could be a tangent line here. There could be a tangent line here. Anywhere on this curve there could be tangent lines. Think about where a tangent line would have a slope or a horizontal tangent line. Think about what the slope would be. That would be where the slope of the tangent line is 0. Think about where this slope would be 0. So if I imagine this tangent line I just drew, if I continued on and see what that tangent line would do as I continued moving my x value up, it would be horizontal at this turning point at the very top of this curve. And it would also be horizontal at this turning point at the bottom of a curve. So this idea right here, determine the points where a function has a horizontal tangent. Those are the turning points, and that actually gives us that's a very quick way of finding those peaks and valleys of a function. So we want to know if it has a horizontal tangent line. It's asking where does the derivative or slope of the tangent line equal 0. So I'm actually going to write that in here. This is asking us to find where does the derivative equal 0. Okay, so because if I know where the derivative equals 0, if the derivative, remember slope of tangent line is 0, then it's a horizontal tangent line, which means that tangent line is at a maximum or minimum. Okay, so you'll see that this is helpful for finding maxes and mins. It just hasn't come out and blatantly said that, but that's what this is doing here. All right, so on this first function, where does 2x plus sine of x have a horizontal tangent line? That would be, again, where does y prime, the derivative, equals 0? That's what we want to know. So we need to take the derivative of this. What is y prime? Well, the derivative of 2x is 2, and the derivative of sine x is cosine of x. So we want to know where does this equal 0? So now we just solve for x. For 2 plus cosine of x equals 0. Well, to get x by itself, first I'm going to subtract 2 from both sides, and then I'm looking to solve where does the cosine of x equal negative 2. Think about that. Where does the cosine of x equal negative 2? If you plug that into your calculator right now and do inverse cosine negative 2, you will get an error, and that's because the cosine of x never equals negative 2. Cosine of x is limited between negative 1 and positive 1. So this never happens. So what does that mean? That means there are no horizontal tangent lines on this function. And if you graphed it, what you would find is there are no peaks and valleys. There are no turns, because if the tangent line never equals 0, then it never turns. So the answer to number 5 is never. Let's find one that does. Okay, so looking at number 6, this is a polynomial. We know it's a cubic. This one definitely is going to have peaks and valleys or maxes and mins. So this function will definitely look more like this first sketch I did, where it does have some ups and downs. So if I want to know where the horizontal tangent line equals 0, again, that's asking for where does the derivative equal 0. So first of all, we need the derivative y prime. We can easily apply power rule here, so bring the 3 down, multiply it by the coefficient of 3, and we end up with the derivative of the first piece, which is 9x squared, minus the derivative of 2x squared, which would be 4x to the first. So here's my derivative, 9x squared minus 4x, and that is the equation of the slope of the tangent line, and we're asked to find where it has a horizontal tangent, which means we want to know where that equals 0. So we just need to solve for x. This is a quadratic, 9x squared minus 4x, but because there's no third term, we can quickly solve for x by just factoring out an x. So we can just say, pull this x out, and I want to know when x times 9x minus 4. Solve for when that equals 0. This will give me two solutions for x from this one, where x equals 0, and from this, which would be when 9x minus 4 equals 0, which is when x equals, add 4, divide by 9. Okay, so when x equals 0, it's got a horizontal tangent line, and when x equals 4/9, it's also got a horizontal tangent line. I'm going to show you a quick visual of this. So here's the graph of 3x cubed minus 2x squared. Let me make it as straight as I can. And you can see at 0, it's got a maximum, a local max. So we've got a local max right here, which means the tangent line would be horizontal, and a little tiny minimum right there as well, which happens to be at 4/9, where it is switching from decreasing to increasing, where that horizontal or that tangent line has to level out as that turn is taking place. So yeah, so that's a visual which is hopefully helping you make sense of our answers of 0 and 4/9. That's where the horizontal tangent line is 0. Okay, I know I told you I'm trying really hard to get these videos to 30-minute video lengths, and I do want to do this last one because it has cosine and sine in it, so I'm going to fly through it. We want to know where the tangent lines of this function would equal 0, cosine x plus sine x. So all we need to do is find where the derivative equals 0. Derivative of cosine of x is negative sine of x. We saw that from the first page of these notes. The derivative of sine of x is cosine of x. So what this is saying is we want to know when negative sine of x plus cosine of x equals 0. That's the derivative. A horizontal tangent line would mean the derivative equals 0. To solve for x, what I'm actually going to do is, since this is negative sine of x, I'm going to add sine of x to both sides, and that's going to give me this equation. Where does cosine of x equal sine of x? Where do the cosine and sine functions intersect, or where do they have the exact same value? What I'm picturing is the unit circle, because we know that they're definitely different here. We're over 1 up 0, over 0 up 1, but you might be remembering the points on this unit circle where sine and cosine were identical, and that was halfway through each quadrant, right here at pi over 4, 3 pi over 4, 5 pi, 7 pi over 4. Wait, no, not identical. They were identical right here. That's it. Because in all these others, one was negative and one was positive. So ignore those, ignore those, ignore those. But right here at pi fourths, those were identical. Oh, and right here. I'm sorry. I'm clearly losing my brain. Right here, too, because they're both negative. So in those two spots, pi over 4, rotation of pi fourths, and 5 pi fourths, sine and cosine have the same values. So that gives us our answer of pi over 4 and 5 pi over 4. And if we graphed this original function, we would see the curves level out or find those turning points at these two x values. Okay, I'm going to stop here. Sorry if I went over 30 minutes, but this would get you through the entire worksheet of 2.2, one of my favorite sections. I hope you've enjoyed this as much as I have. Okay, see you next time.